Okay, so we're talking about exponential growth. Let's just have a little talk before the quiz. We're talking about exponential growth. And so, what is the centerpiece of exponential growth? What is it all about? Okay, yeah, so we talked about for a given exponential covariation of two quantities, the growth factor is kind of the central value or the central idea behind exponential growth. Okay, and so what is a growth factor? What is it? Yeah, it's a multiplier, right? So it's something we use to multiply. Can you be more specific? It's a multiplier on output to get input, right? Output, you multiply it on output, it gives you the input, right? No, that's not right. You multiply it times the output, it gives you the next output, right? So that's how something grows exponentially, by repeated multiplication by the same number. By repeated multiplication by the same number. So if your initial value is 5 and your growth factor is 2, then what's your next value of the quantity? Start at 5, your growth factor is 2. The next value of the quantity is 10. And then the next value of the quantity is 20. And then the next value of the quantity is? Not 30. 40. Then the next value is 80. You keep multiplying by 2. If 2 is your growth factor, whatever quantity is growing exponentially, you just keep multiplying by 2. This is what exponential growth is about. Okay, it's a multiplier on output to get another output. Okay, what we've learned so far is the growth factor is the multiplier on an output to get the next output, right? So if we advance the input by 1, we'll get that next output when we multiply. Okay, what stays consistent from output to output? Well, of course, the growth factor. Okay, the ratio stays consistent. We started talking about it last time in class. So if you have a growth factor, then you also have a constant what? Not rate of change, not constant rate of change. Percent change. If we have a growth factor, then we have a consistent percent change. Percent change. Constant rate of change is where we have a consistent amount of change, right? Like the amount that you add every time would stay the same. But here, what we are multiplying by stays the same. That results in a consistent percent change. Get the difference? Constant rate of change, remember, was additive growth. You always add the same amount. Exponential growth, you always multiply by the same amount. So you get a consistent percent change. And then remember we saw this last time, that growth factor then is 1 plus the percent change, where R is a decimal version of the percent change. Okay, questions? Okay, did y'all get 1 through 3 right? I left it on the screen. That was 1 through 3 right there. Just talked about it. I left it on the screen. This is all about a growth factor, or this all applies to decay too, right? So same with decay. Growth factor or decay factor. It's a multiplier on output to get the next output. The multiplier on output to get the next output. One extra, thanks. Okay, and what stays the same? What stays the same when it comes to exponential growth? Percent change. What is the same when it comes to linear growth? You have a constant rate of change. You have a constant rate of change. Constant percent change with exponential growth. Okay? So, the last question here, I've kind of set it up here. It said after 5 hours, there were 3075 bacteria. And after 6 hours, 2492. And it says we want to know how many. So X would be the number of hours since applying the chemical. Okay, X would be the number of hours since applying the chemical, and Y would be then the number of bacteria. Okay, and so how can we get the number at 11 using this idea? So using this idea of growth factors as a multiplier, how can we get it at 11? Well, first we need to get that growth factor, in this case a decay factor. So we're asking, what number would you multiply the output of 5 by to get the output at 6? How would you get that decay factor? What do you have to multiply 3075 by to get 2492? And that would be equal to 2492 divided by 3075. So whatever that turns out to be. So what number would you have to multiply 3075 by to get 2492? It'd be that ratio, 2492 divided by 3075. Let's get an approximation for that. Point what? 0.81. So I've got my decay factor, 0.81. Without making a function, how can I get the number of bacteria at 11 hours? I can start here at 6, and how would I get from 6 hours to 11 hours using my decay factor? I'd multiply by 0.81. How many times? 5 times. Every time I multiply by 0.81, it tells me the bacteria in the next hour. So if I multiply by 0.81 5 times from the number at hour 6, it would give me the number at hour 11. So I'm going to take 2492. I'm going to multiply by 0.81 5 times. Every time I multiply by 0.81, it advances me to the next hour, and I want to get to the 11th hour. The 11th hour. So it's like, so that's why we have exponents, just to make that. I don't want to write 0.815 times. That's what an exponent's for, just to make our life easier. But this is really about multiplication. This is really about multiplication. Multiplying by 0.81 5 times. All right. Similarly, if I want 3 hours, what could I do? Take 3075 and divide by 0.81. I'm going to go backwards. And then divide by 0.81 again, twice. And that'll get me the number of bacteria at 3 hours. So I would take 3075, and I would divide by 0.81. And then take that. That would be the number at 4 hours. And then I would divide by 0.81. Which is the same as 0.81 to the negative 2. If you said times 0.81 to the negative 2, that's exactly the same thing as this. So this is the number at 11 hours. This is the number at 3 hours. Repeated multiplication of the growth or decay factor. That's the name of the game. That's the name of the game. It's not about just figuring out what the formula is and turning your brain off and just finding numbers from the formula. You really got to know what it's all about, what's happening. What's happening is you're multiplying the output by this number to get the next output, and that happens over and over again, generating outputs each time. Okay, so let's practice a little bit more of these, the relationship between the growth and decay factor and the percent change. Any questions about the quiz? Yeah.
You've got the same answer in 3075 times 0.81 to the 11? Or is that a different?
No, because you're starting at 5. If you did 3075 times 0.81 to the 11, what hour would you be at? Hour 16. You found the number at 16 hours. So if you want to use the 3075, you do 0.81 to the, how many hours do you need? 6. You need 6 hours from hour 5 to get to hour 11. So that would work too. Okay? Yeah, so there's other possible ways to get these. This is just kind of the one way. Any more questions about the quiz? Okay, so I got a couple examples here. So I'm going to give you the growth or decay factor. You're going to find the percent change. This is what we ended up with yesterday, or Tuesday. This is a growth or decay factor. You're going to find percent change. Go. There's four examples. This is really, really important that we have this. So this is our multiplier. In each case, it's a multiplier on output to get the next output. What's that consistent percent change in each case? What's that consistent percent change in each case? Here's the key. So here's the key to thinking about this. Growth factor is 1 plus the percent change. Okay, Vince, how about that first one? Is it, first of all, growth or decay? Decay. Okay, so then what is the percent change? If that's decay, then what does that number mean? Is that how much it decays? Is it 65% that we lose every time? Okay, 1 plus what? 1 plus what? Do you know? So if you can't do it in your head, which is okay, some of them you can't. Some of them you can't just do. So just make that R and just solve for R. What would you do to solve for R? Okay, so yeah, is it but 0.35? Negative. So yeah, so it's 35% what? Decrease. 35% decrease or negative 35% change. So if you declare that it's decrease, you can call it positive. You call it positive. Okay? But if it's change, then it's negative. The amount of change is negative. Okay. Next one. Tyler.
Which one?
Next one. 1.17.
Which Tyler?
Oh, right here. Tyler Brady.
0.17.
0.17. Is that growth or decay?
Growth.
He wants growth. So the percent change is?
17%.
17% increase. 17% increase. Did you get it? All right. 4. Let's see. Matt, right? Tell me. For 4. Okay, what's the percent change? Is that growth or decay? Growth. What is it? 300%. Why? Because when you quadruple, when you multiply by 4, you keep the one from before, and the amount of increase is threefold. So when you multiply by 4, the amount of increase is 3. Because you have what you had before, plus now 3 or 300% additional. So this is a tricky one. Students will often say, oh, it's 400% increase. Well, you haven't taken into account what you started with. What you increase by is 300%. Does it make sense? All right, 0.21. Let's see. How about Bill? The last one. 0.79. So what's the percent change? The percent change is 0.21. Or is it 0.79? What's the percent change? So this is, with decay, it's really important that you know what that number means and what that number means. Which one is the percent change? Which one's the percent change? This, 1 plus the percent change, right? 1, so and is that right? Is it 0.79? Negative. So the percent change is negative 79%, or 79% decrease every time. So what's the 0.21 about? What's that number mean? Or 21%. 21% means what in the situation? Okay, it's the decay factor, but what does it mean for our amount? Yeah.
What's left over?
What remains? What's left over? What you keep? What you keep every time. We're going to multiply by 0.21. That's going to grab 21% of what we had before and hold on to it. So we just lost 79%. So a decay factor, its meaning is what you keep every time. The portion that you keep or the portion that remains. Okay, any questions on that? So it's really important that you can go back and forth between these multipliers, whether decay or growth factor, and then the corresponding percent change. Okay, so what's next? Oh, okay, so let's apply that. And you had in your web work, number 6. So number 6, let's talk about that. So now that we just practiced that, let's put it. Oh, jeez. Where is it? Where are you there? Okay. So let's put it to work here. So what we just did, now we apply it to the real world. So the percent of a lake surface covered by algae, initially at 35%, was halved each year since the passage of anti-pollution laws. Is this constant rate of change or exponential growth? Is this constant rate of change or exponential growth, first of all? So let's have you go through. You're going to do 2 things each time. You're going to answer the question, is it constant rate of change or exponential growth? And then secondly, or decay. And then secondly, if it's, so then what is the corresponding growth or decay factor? If it's exponential growth or decay, what's the corresponding growth or decay factor? If it's constant rate of change, what's the value of the constant rate of change? So 2 questions. Exponential or constant rate of change? That's the first question. And then second question is, what's the value? What's the value of the multiplier or the constant rate? Value of the growth factor or decay factor, or the constant rate, if it's constant rate of change. So you're going to answer those 2 questions for each of 1 through 5. Okay? Go. Give it a shot. You can work together. Talk about it. I'll be right back to call on some of you. Okay, Melise. Where's Melise? Where is she? Not here today? Oh, that's right. She's in a tech meet, I think. I got Tyler. Where's Jeanette? Jeanette? There's Jeanette. Okay, how'd the first one go? Exponential growth. Okay. Yeah. Okay, so it's initially at 35% and it is halved each year. That's the key. Halved each year. So they kind of gave you a decoy here, right? That's just saying initially it was 35%. It's getting the initial value, but it happens to be a percent. The key is it was halved each year. So your decay factor is? Decay factors won't be negative because you're going to multiply, right? So we're looking for the decay factor. So you should have got your decay factor was 0.5. What's negative here? Not the decay factor, but what's negative? Percent change. What's the percent change? Percent change is negative 50%. So we keep half of it. That's what this does. This keeps half. Then the rest of it is what we lose. We lose 50%. You keep 50 and you lose 50. So the decay factor is 0.5. You multiply by 0.5. Your percent change is negative 50%. Okay? How about Nada? Next one. Exponential or constant rate of change? All right? Decay or growth? Okay? What is the decay factor? 0.3. What do we think? That's what, yeah, so 30% is the percent change. 0.7 is kept, right? Your decay factor is how much you keep. If your decay factor is how much you keep and you're losing 30%, you're going to need that decay factor to be 0.7. How many people got that before we started talking about it? Not enough. So this is why it's so important. You can read a question and you're given something, you have to know, is it the percent change or is it the decay factor? They're giving you the percent change. They're saying it goes down 30%. Therefore, your decay factor would be keeping 70% or 0.7. All right, next one. Flora. What about this next one? It says each filter removes all but 30% of the remaining impurities from the water. Decay or growth? Decay. What's the decay factor? You want 0.3? So she wants 0.3 for this one. What do you think? It says it removes all but, meaning you keep 30%. Decay factor 0.3. That's right. Decay factor 0.3. Because it's telling you how much you keep. Right? It's telling you how much you keep. The previous question, it was telling you how much you lost. Okay? Over the course of the next 50 years, the town grew at a rate of 250 people per year. Exponential or linear? Linear. What's the constant rate of change? 250 people per year. Additive growth, right? Every year, you would add 250. Not multiply by something, you would add 250. Linear growth. Okay? Last one. Exponential or linear? The town grew at a rate of 10% per decade. Exponential, growth, or decay? Growth. Growth factor is 1.1. It's giving you the percent increase. So what do? You're going to add 1 to that. You're going to add 1 to that to get 1.1. You're going to multiply by 1.1, which would result in 10% increase every time. Okay, any questions on that? Really important. Okay, so here's the setup we want to ask some questions about. So a population of a colony, function named P, it grows 21% every week, where X is the number of weeks since the initial observation of the colony. Okay, so here's kind of a conceptual question, all right? If you know the population 7 weeks after the initial observation, how can you represent the size of the colony 9 weeks after the initial observation? So this is, again, do you understand what's going on? And then can you use things we've learned to represent P of 9? Okay, so P of 9 is, that's an output when the input is 9, so that's the population of the colony when X equals 9. So, given the fact that it's growing 21% per week, and we know what the population is 7 weeks after the initial observation, can you write an expression that would find the population 9 weeks after the initial observation? Okay, work on it. See if you can do it. Do you understand what's going on? This is, check your understanding. So setting up this is not allowed for this exercise. This is to check to see if you can use the principles and ideas. All right. So setting up a function and using the plugging in and cranking something out, that's not allowed here for this question. Okay, so if you know the population 7 weeks after the initial observation, and it grows 21% per week. How can you find the population 9 years or 9 weeks after the initial observation? Where's Alexis? Alexis Bradley. Where's Jared? Jared, how'd you do on this? What do you think?
I can really figure it out.
Okay, well, how about this? So the population 7 weeks after the initial observation. Can we just represent that? How do we represent that? P of 7. All right, so getting P of 9 has to do with what we know, right? We know P of 7. So what could you do to P of 7 to get P of 9?
P of 9 minus P of 7.
No, not subtraction. So we're starting with P of 7. We're saying, what do we do to P of 7? What do we do to that population 7 years? What's that? Times 0.21. Is that what we want to do? Times 1.21. Does that do it? What is that? What would that give? That would be the population after 8 weeks. So, what do we do? Do it again. How many people got it before we started? Oh, so about half.
Okay, can you explain to me what you mean not P of X equals A times B
Yeah.
X is not allowed?
Right. Oh no, this is totally different. This would be like figuring out what the population was at 0. That's what A is. A is what the population started at after 0 weeks. And then doing 1.21 to the, so coming up with this formula and then saying, oh, I want P of 9. So P of 9 equals A times 1.21 to the 9th. Never knowing anything what that 1.21 means. That's what I mean by that. Yeah.
We did P of 7 times 1.21 squared.
That's where I'm going. That's where I'm going. That's the same thing.
It's not too close to the formula.
No, that's the same thing. That's perfectly, that's where we're going. So she said, isn't that the same thing as P of 7 times 1.21 squared? Yeah. Okay, so let's find, what is 1.21 squared? Let's do that. What is that? Equals 1.461. So this is the same as P of 7 times 1.461. 4641. Okay, so notice something here. I just took an output, and I multiplied by a number, and I got another output. Was it the next output? No, what was it? It was like 2 outputs later, right? So I've got an output, I multiply by this number, and I get the output 2 inputs later. So this is a growth factor, because why? Because it's a multiplier on output to get another output. But it's not the next output, it's 2 outputs later. So we call this the 2-unit growth factor. The 2-unit growth factor. So what does the 2 refer to? The output or the input? The output or the input, the 2. What is that referring to? Does it have to do with the output or the input? The 2. It's what the input did, right? So the input went from 7 to 9. We advanced 2 units of input, and by multiplying by this growth factor, it gave us that corresponding output for 2 input units later. Do you see? So it's still a multiplier on output to give another output. We see it right there. Times an output. Times an output to get another output. But the 2-unit growth factor means that we're advancing an input by 2. We advance an input by 2, in this case from 7 to 9. So there could be a 3-unit growth factor, there's a 5-unit growth factor, an 8-unit growth factor. So really, for a given situation, we've just been talking about the growth factor so far. But really, for any given situation, there's a whole list of growth factors and decay factors that apply to a given context.
So can you say that 2-unit growth factor is pretty much the exponent?
It's not an exponent.
What I'm saying, but so the 1.21 is you multiply that by 2. So if you say it's a 5-unit growth factor, would you say that's the 1.2 to the 5th?
Right, so the 5-unit growth factor would be, what number do we need to multiply by to advance us 5 units of input? Well, we would need to multiply by 1.21 how many times? 5 times. So the 5-unit growth factor would be 1.21 to the 5th. Because we would think about multiplying by 1.21 times the output 5 times in succession. That brings us ahead 5 units of input, gives us the output 5 units of input later. Does it make sense? All right, let's practice this. Any questions? So now what we're getting into is what we call multi-unit growth factors or decay factors. Multi-unit growth factors. So that's why you're so before, when we talked about the growth factor or the decay factor, we were talking about what? We were talking about the 1-unit growth factor or the 1-unit decay factor. But we didn't specify that because it was the only factor we were talking about. But now that we know that there's many growth factors for a given context, we specify that the one that we talked about before as the 1-unit growth factor. It gives us the next output rather than skipping ahead outputs. Like the 2-unit would skip ahead 2 outputs. 5-unit would skip ahead 5 units. Or skip ahead 5 outputs. So let's practice this. So here's an airborne disease starts to spread such that the cases grow exponentially. And we have the number of cases after 3 days and the number of cases after 4 days. Okay, 174 cases after 3 days, 186 cases after 4 days. So I have a series of questions for you. So here are the questions you're going to work on for this situation. Find the 1-day growth factor, okay? Then find the 3-day growth factor. Find the 3-day percent change, okay? Write the function for the number of reported cases after X days. And then if N is the number of 3-day periods, write a new function that gives the number of reported cases after N 3-day periods. So I'm going to do attendance. So you work on this together. Work on these questions. Let's see, Katie. Is this Katie? Katie, how did the 1-day growth factor go? How did you find the 1-day growth factor? $174 divided by 186. What'd you get for that? So 0.94. Would that be growth or decay? 0.94. Decay. Is this decay or growth? So yeah, so you get that. That's good. So go for that, but then check it, right? So is 174 times your 0.94, is that going to give you a bigger number? 0.94 is going to take 94% of it and give you a smaller number, but we're growing. So you had the right idea. So how are you going to change what you did? Yeah, it's going to be 186 divided by the 174. That's going to give you what you multiply 174 by to get 186. So we're looking for this multiplier here. What do we multiply 174 by to get 186? 1 point? 0?
Are we rounding or not? 6, 8.
Let's round it 3 decimal places. 6, 8? 6, 9. Let's do that much rounding. So 1.1, that's rounding too much. The 1.1 is not close enough. 1.068, so doing 3 more decimal places is too many decimal places. So what's reasonable? 2, 3, or 4 decimal places would be reasonable. But listing out 5 or more decimal places is not necessary. And doing 1.1, that's not close enough. That's too far off the mark. Okay? So 1.07 would be acceptable. This is a little bit better, 1.069. All right, so how do we get the 3-day growth factor then?
Big question.
Yeah, please.
For the outcomes, how do you want us to round to 3 decimal places as well?
It just kind of always depends on the situation. Like there's no hard and fast. So what you mean the number of reported cases?
Yeah.
Well, no, that's going to be people. So that's going to be you're going to round to the nearest person. Yeah, you don't want to use any decimals there. Okay. All right. So 3-day growth factor. So what would say here I am at 4 days. What would I multiply by if I wanted to multiply just by one value to get the number of cases at 7 days? And how'd you get that? Yeah, so if we want to advance 4 days, it's like multiplying by 1.069. Sorry, 3. If we want to advance 3 days, we're going to multiply by that 1.069 3 times. So it's going to be 1.069 cubed. And so let's get an approximation for that. Put down here. We'll do that. So 1.221. 222. Two or 1? Okay, what's the 3-day percent change then? The 3-day percent change comes from one thing and one thing only. It comes from the 3-day growth factor. It doesn't come from anything else. If your 3-day growth factor is 1.222, what's your 3-day percent change? 22.2, just like the way we did it before. All right. So notice the percent change for 1 day is 6.9. Could you multiply that 6.9 times 3 to get the 3-day percent change? Would it work? So you might think that if I've got the 1-day percent change, all I need to do is multiply that by 3, and that would give me the 3-day percent change. Does it work? So we're at about 7%. 7% 1-day increase. 7% times 3 is 21. In fact, we'd be a little bit less than 21. But what's the true 3-day percent change? More than 22. So that doesn't work. The 3-day percent change comes from one place and one place only. The 3-day growth factor. So you get your percent change from the corresponding growth factor. Don't get it from another percent change because that doesn't work. And we'll get into more of that next week. Okay? We want the function now, f of x. F of x. So what do we need for that? We need the initial value, and then we need the 1-day growth factor, which we already have. So we'll write that down, 1.069. And then for as many days as go by, we're going to multiply by that many 1.069s. That's what the exponent does, right? It tells us keep multiplying by 1.069 x times. X times. How are we going to find a? Okay, so if we were at 174, what would we do to work backwards and get the number of cases at 0 days. Divide by 1.069, how many times? 1, 2, 3 times. If I took the 174 and I divide by 1.069 and then again and then a third time, that would give me the initial value, or the number of reported cases at 0. And I think when you do that, you get don't touch the writing pad. 142? Should get 142. So that allows us to write this function now. 142 times 1.069 to the x. So that's the function. Okay, now we want to write a function g of n in that gives it to us in terms of the number of 3-day periods. So what's the initial value? Doesn't change, right? We're just going to go by 3 days instead of 1 day. That doesn't change what the initial number of cases is, 142. All right, so if we raise it to the n, so what growth factor are we going to use if n is a 3-day period? Yeah, so you're going to use the 3-day growth factor. So you want your exponent and your growth factor to match, right? If this is what happens every 3 days, well then its exponent should be n, the number of 3-day periods. Okay, so I want you to, one more question about this one. So find the output for x equals 17, but I want you to be creative and do that in different ways. Apply your understanding of exponential growth to do this. So let's just get the obvious one out of the way. What's the obvious way that we can find the number of cases after 17 days? It would be f of what? F of 17, right? F of 17, which you would do 142 times 1.069 to the 17th, because it's like starting with 142 and multiplying by 1.069 17 times. 1 time for each day. So we'll just get that one out of the way. Okay? So now I want you to come up with a couple more ways that something different than this that could generate that same output, that number of cases on the 17th day. Use the idea of exponential growth to do it. See if you can do it. Okay? We'll see what you come up with in a second. Like, for instance, use this value. Could you get it using this value? That's what I mean. Say start with 186. Could you find the number of cases after 17 days using the 186? Okay, let's see what you came up with. Angelica, did you come up with any ways to do this? Come up with this value of cases at 17 days. And there's some way different than this. You want to do what now? I think that was right. Tell me again. 186 times. Okay. Does it work? Who's got another way? You're dying to share. Yeah, tell me. F of 17?
No, I'm 14. Oh, okay. Well,
It's still F of 17. But what you said was right. F of 17 is 74. 1.069. 14th. That works. Anybody use the G function to do this? Yeah.
So I did G of 5.
G of 5.
And then it's the times the F or G. Oh wait.
So G of 5 would give you what? How many days?
17. Or no.
5.6.
It would give you 15 days. Now this would be the number of cases at 15 days. Now how can we adjust that to get 17?
That was confusing. So it would be 5.6.
No, don't do that. I mean, yeah, that works, but that just take 15 days and go from there. So how can you adjust the 15 days?
So from the
Hold on, give him a second.
second day, so it would be F of 2.
You don't want to use F of 2 because that's this number.
Okay.
Just use your growth factor. Use your growth factor.
So
So we're at 15 days, and we want to advance 2 more days.
it'd be so it'd be 2 times. Oh,
This gets us ahead 1 day, right?
sure.
So we want to go ahead 2 days.
So 1.069 to the second.
Yeah. All right, well, let me just write it out. So you could take G of 5, which is at 15 days. You can multiply by 1.069 and then 1.069 again to get 17 days. There's a dozen different expressions we could write to get this. Anyone dying to share one more? G of what? G6. Does it work? What is G of 6 going to give us after how many days? How many cases? 18. So this is how many cases after 18 days. So we divided by the 1 day growth factor, which pulls us back 1 day to the 17th day. That'll be the number of cases on the 17th day.